Welcome back to Summarize Science. Today we're talking about a problem that's becoming all too common in cities around the world: flash flooding. When intense rain hits our towns, the storm sewer systems designed to protect us can get completely overwhelmed, leading to dangerous and costly floods. The big challenge for city planners is, how do you effectively monitor these massive, complex, and hidden underground networks? Putting a sensor on every pipe is just not feasible. It's too expensive and impractical. But what if you didn't have to? This is where a new study comes in, with a clever idea called a data-driven sparse sensing approach. In simple terms, it's about being smart, not just using more stuff. Instead of guessing where to put sensors, the researchers used a powerful computer model to simulate thousands of different storm events. This created a massive virtual dataset of how water would flow through a real storm sewer system under all sorts of conditions. The test site for this powerful technique was the Woodland Avenue catchment in Duluth, Minnesota, a real-world network with steep hills that make it particularly prone to flooding. Using all that simulated data, they then applied advanced mathematical techniques to ask a simple question: if we can only place a few sensors, where are the absolute most important spots to get the biggest bang for our buck? The algorithm crunched the numbers and identified the optimal locations that would give them the most information about the entire system. The results of this quality over quantity approach were pretty stunning. First, they confirmed that placing sensors in these few, optimally chosen locations was dramatically better than placing them randomly. In fact, random placement often led to completely useless data, highlighting that it's not about how many sensors you have, but where they are. And here's the headline finding. Out of 77 possible locations in the network, just 3 strategically placed sensors were enough to accurately reconstruct the water flow across the entire system. To put that in perspective, that's using less than 4% of the possible sensor locations to get a full, high-accuracy picture. The accuracy was over 92%, which is an incredible result for such a minimal setup. But the real world isn't perfect, so they also tested the system for realistic problems. What if the sensor readings are a little noisy or inaccurate? They found that even with up to 15% artificial noise added to the measurements, the system still performed remarkably well. They also simulated what would happen if a sensor completely failed. While losing certain key sensors did impact performance, the system's overall stability improved as more sensors were added. Interestingly, the most critical sensor in a failure scenario wasn't always the one the initial algorithm ranked as number 1, showing how crucial it is to test for real-world robustness. So, let's recap the important points here. First, you don't need a massive number of sensors to effectively monitor a complex storm drain system. Second, being incredibly smart about where you place those few sensors is the absolute key to success. And third, this data-driven method is robust enough to handle the messiness of the real world, like measurement errors and equipment failures. What could this mean for the future? It opens the door for cities to develop highly effective, low-cost flood monitoring networks. This framework could be integrated with predictive models to create powerful early warning systems, giving communities critical time to prepare for a flood and potentially saving property, infrastructure, and even lives. Thanks for watching Summarize Science.